All right, so here are the notes for section 11.1, limits in motion, the tangent problem. So the first thing we've got is average velocity, which is the change in position divided by the change in time. So example 1, the automobile travels 120 miles in 2 hours, 30 minutes. What's its average velocity over the entire 2.5 time interval? So change in position is going to be 120. Change in time is going to be 2.5. So their average speed is 48 miles per hour. So relatively straightforward. All right, so limits revisited. So example 2, ball rolls down a ramp so its distance from the top of the ramp after t seconds is exactly t squared feet. What's its instantaneous velocity after 3 seconds? So we can do this a couple different ways. We can kind of let our two times get super close together. So for example, we'll take the interval 3 to 3.1. So this is x2 and x1. So on the bottom we'll have 3.1 minus 3, the change in time. Change in position would be 3.1 squared minus 3 squared. And if you work this out, it comes out to be 0.61 over 0.1, which is 6.1. And I can keep repeating this process and let the second time get closer and closer to the first and look at what this number is trending towards. So this would be 3.05 squared minus 3 squared over 3.05 minus 3. If I work this out, I get 0.3025 on top, I get 0.05 on bottom. This comes out to be 6.05. So it looks like they're trending towards 6. But if you look at it in terms of a limit, what we can do, we're going to let the limit as t gets close to 3. So essentially this is just doing this step over and over again, letting the second time get closer and closer to the first time. Now, since I'm doing this in terms of variables, the top is just going to be t squared minus 3 squared over t minus 3. Now this is a difference of squares, so this becomes the limit if t goes to 3, of t plus 3, t minus 3, all over t minus 3. So t minus 3's can cancel, give me the limit as t approaches 3, of t plus 3, which is 6. So the instantaneous speed is 6 feet per second. Now, this step here only works where I cancel the t minus 3's out because I'm doing a limit. If I set t equal to 3, I can't do that division because then it's 0 divided by 0, which isn't allowed. So that canceling step only works because I have that limit step. So the informal definition of a limit, start the limit as x approaches a if f of x equals L, meaning that f of x gets arbitrary close to L as x gets arbitrary close, but not exactly equal to a. So when you're calculating the slope, you can't have your 2 points on top of each other. Otherwise, you don't have a delta x, and it becomes 0 on the bottom. Okay, so connection to tangent lines. So example 3, use limits to find the slope of the tangent s equals t squared at the point 1, 1. So what we're going to do is we're going to the limit as t approaches 1 of t squared minus 1 squared over t minus 1. So that's y2. So we're going to put some arbitrary point here and let it move towards that one. So y value is just whatever t squared is, or the t s value. And 1, 1 is the coordinate that I know. So there's some point here that's at t comma t squared. And I'm going to let that t get closer and closer to 1. So y2 minus y1, x2 minus x1. So just like before, I can factor that numerator. That's t plus 1, t minus 1, all over t minus 1, which then lets me cancel. It just gives me a t plus 1, which is 2. So that's the slope. Okay, average rate of change, so delta y over delta x, so f of b minus f of a, so this is essentially y2 and y1, x2 and x1. Geometrically, this is the slope of the secant line, so a line that touches 2 points. So x1, y1, x2, y2, because a function value is the same thing as y. Okay, so definition of derivative at a point. The derivative of function f at x equals a, is denoted by f prime of a, read f prime of a, is this, provided the limit exists. Geometrically, this is the slope of the tangent line through the point a comma f of a. easier for computing. So the derivative function, sometimes you'll see it written like this. F prime of a, once again, f of a plus h minus f of a all over h. So find f prime of 4 if f of x equals 2x squared minus 3. So let's see here. So we're doing f of 4. So this is our a value. So our formula is going to be the limit as h approaches 0 of f of 4 plus h minus f of 4 all over h. So the limit as h approaches 0. So f of 4 plus h means plug 4 plus h in for the x's. So it becomes 2 times 4 plus h squared minus 3. So all of that is this. Minus f of 4 is what you get when you plug 4 into this equation. So if I plug 4 in, that's 16. 2 times 16 is 32, so minus 29. Right? Yep. All over h, which is still unknown. So I can expand this. So that's going to give me 2 times 16 plus 8h plus h squared minus 3 minus 29 all over h. And I could distribute the 2. So 32 plus 16h plus 2h squared minus 3 minus 29 all over h. And if you look at your numbers, they should actually all cancel out. 32 minus 3 minus 29 all goes away. So I have this, and I can take an h out, so this is 16 plus 2h. So if h is going to 0, this becomes 16 plus 2 times 0, which is just 16. So the value of the derivative at 4 is equal to 16, which means the slope of the tangent line at 4 comma 29 is 16. Alrighty, so here's another definition. So this is find the generic. Notice this is still x now, so this will give us a formula as our answer. So find f prime of x if f of x equals x squared. So similar setups. So the limit as h goes to 0 of f of x plus h minus f of x all over h. So the limit as h approaches 0. So f of x plus h means plug x plus h in for this x. So x plus h squared minus f of x is the original, the original equation, minus x squared, all over h. So expand this guy. I'm going to do it in my head. It's going to be x squared plus 2xh plus h squared minus the x squared all over h. So you look, your x squareds go away. Whee, those cancel. And I can drop an h out. So 2x plus h becomes 2x plus 0 becomes 2x. So this is the generic derivative of my function. The reason this is helpful is that this lets me calculate the derivative at any point if I do the algebra first without having to rerun the limit step over and over again every time I change my x value. So if I want to know the derivative at 1, I can just plug 1 in here instead of doing 1 plus h, expanding and reducing and getting just 2. Or if I want to know when the derivative at 3, instead of doing 3 plus h, I can just plug 3 in down here at the end. Okay, so dy dx is the same thing as the derivative, so it's going to work in a very similar manner. So we start the same way. The limit h approaches 0 of f of x plus h minus f of x all over h. So the limit is h approaches 0 of 1 over x plus h minus 1 over x all over h. So we need to combine these fractions. So we need a common denominator. This one needs to be multiplied by x. This one needs to be multiplied by x plus h. So I have this. So now I can combine my two fractions. So this becomes x minus x goes away. So just negative h over x plus h all over h. So divide by h is the same thing as multiplying by its reciprocal. So times 1 over h. So we're going to come back up here. So this becomes the limit as x approaches 0 of negative 1 over x times x plus h. But if h is 0, this becomes negative 1 over x times x plus 0, which is negative 1 over x times x, which is negative 1 over x squared. So this is my derivative function. And that brings us to the end of the section.